In early September 1859, the night sky over much of the globe suddenly erupted in color. The auroras were so intensely bright that people woke up and began their morning routines, convinced the sun had already risen. This invisible force surged directly into the cutting-edge technology of the era. Telegraph networks went haywire, machines sparked, paper caught fire, and the telegraph operators were physically shocked by the intense electrical current surging through their equipment. A storm of that same intensity hitting the Earth today encounters a world woven together by thousands of miles of high-voltage transmission lines and sensitive microelectronics. By anchoring our society to a constant flow of electricity, we have increased our exposure to these solar surges, creating a level of technological risk that was non-existent during the 19th century. Viral internet rumors claiming that the sun is becoming unstable or preparing to explode are false. The sun actually operates on a predictable 11-year magnetic cycle. We are currently moving through the peak of that cycle, a period scientists call solar maximum. We track this peak by watching for the appearance of complex magnetic regions on the solar surface, known as sunspots. As the cycle reaches its climax, the sun's magnetic north and south poles completely flip, acting as the primary engine for violent space weather. The sun is behaving exactly as it should, operating as a functioning magnetic engine that happens to aim its peak activity directly toward our planet. A solar storm begins when magnetic field lines on the solar surface twist under immense pressure until they violently snap and reconnect. The first hazard is a solar flare, a flash of light and radiation that reaches Earth in just 8 minutes, traveling at the speed of light. The flare is often followed by a coronal mass ejection, or CME. This is a billion-ton cloud of solar plasma that takes several days to cross the gap and reach us. Earth's magnetic field serves as our first line of defense, catching these charged particles and funneling them toward the north and south poles. As these particles collide with oxygen and nitrogen in our upper atmosphere, the chemical reaction causes the sky to glow. The vibrant ribbons of the aurora are the visible evidence of our planet's magnetic field actively deflecting a solar surge. An extreme CME can overwhelm our magnetic shield, first bombarding satellites with high-energy radiation. Simultaneously, solar X-rays heat the upper atmosphere, causing it to swell. This creates enhanced drag, slowing satellites down and pulling them toward Earth. This disturbance disrupts global GPS, grounds commercial flights, and crashes navigational networks. When the storm reaches the ground, its impact is determined by a bedrock lottery. Geology dictates how a region handles currents induced by shifting magnetic fields. Because granite is highly resistive, electrical current cannot dissipate. Instead, it surges upward, directly into power transmission lines. Surviving a space weather event depends as much on the geological bedrock beneath your feet as it does on the sky above you. A direct hit could melt the copper wiring inside high-voltage transformers, causing regional blackouts that last for months and disabling water supplies and hospitals. To mitigate this risk, space weather forecasters at agencies like NOAA and the USGS monitor the sun 24 hours a day. Their early warnings provide the crucial hours and days needed for utility companies to prepare their infrastructure before the CME arrives. These warnings allow operators to shut down sensitive power grids and reroute polar flight paths to protect electronic systems. Space weather forecasting provides the tools to protect the electrical foundations of our society, allowing us to witness the sun's peak magnetic activity as a spectacular atmospheric display.